Chapter 3 is all about bonding. Ionic and covalent compounds, how we put them together, and what exactly they look like. So when we're talking about bonding, we're talking about putting two or more atoms together so that they basically stick together. In order to do this, atoms need to either gain, lose, or share electrons. So electrons are really what is causing the bond between two atoms. And in an ionic bond, one of the atoms will gain an electron and the other atom will lose an electron. So if you look at the top picture, we see an ionic bond. So we have one atom here, atom number 1, which is a metal. We have atom number 2, which is a nonmetal. Atom number 1 is going to lose an electron and give it to atom number 2. Atom number 1 then becomes positively charged. It loses a negative charge. So if it's a neutral atom and it loses a negative charge, it then becomes positive. Atom number 2, B, becomes negatively charged. If it was a neutral atom and it gained a negative electron, then it's going to become a negative atom. So this positive charge is attracted to this negative charge, and then these two will stick together. So that's how this ionic bond works. One atom gives up an electron, the other one gets an electron, they become charged, they become what we call ions. And when they're ions, opposites attract. The positive ion is attracted to the negative ion, and then they stick together. In a covalent bond, we're looking at sharing electrons. This is a bond that would happen between two nonmetals. So the ionic bond is between a metal and a nonmetal. In a covalent bond, you're going to see two nonmetals. So a nonmetal and a nonmetal, or a nonmetal and a metalloid. So you're going to have, in the covalent bond, you'll have electrons that don't have a pair. So you see these pairs here, here, here. We've got an electron here that's just kind of chilling, hanging out by itself. It doesn't have a pair. It doesn't have another electron with it. So these two, both of them, have unpaired electrons. Well, if they share these two electrons, then each atom will then have 8 electrons around it if these two are shared, right? And really that's what ultimately all atoms want. They want 8 electrons around them, around the outside. So in all of these cases, what these atoms are really doing is trying to get 8 electrons on the outside in the valence shell. That's sort of the goal here, because that's the most stable. So in ionic bonding, we have charged ions. And what's interesting about charged ions is that they are water soluble, meaning they can dissolve in water. Water can dissolve them. So in this case, we've got sodium chloride. Sodium has 1 valence electron. Chlorine has 7 valence electrons. They both want 8. So 1, way too low. 7, close, but not quite there. So what happens is the sodium loses an electron and gives it over to the chlorine. The sodium then becomes positively charged. The chlorine then becomes negatively charged. These two are then attracted to each other through those electrical charges, positive and negative attract, and then they stick together. This forms salt. Basic table salt is NaCl, or sodium chloride. In ionic bonding, you're going to see an IDE ending. So for NaCl, we have sodium chloride. for stannous fluoride, SN is tin, but we call it stannous fluoride. We have that IDE ending. It's important to know that atoms always want a full outer shell. Depending on what their valence shell is, they usually want 8 electrons in the outermost shell. In order to do this, they could lose electrons or they could gain electrons. A positively charged ion, a positively charged atom, is called a cation. These are the ones that are donating electrons. They give up an electron, they become positively charged. Those are cations. Anions are the opposite. These are the ones that become negatively charged. They gain electrons. They pick up electrons in order to become negatively charged and fill their outermost shell. Opposite charges attract, and that's important because that's how these molecules are going to be forming, through these charged ions attracted to each other. Group number in the periodic table is going to generally correspond to the charge of the atom. This is not something that you really need to memorize. I'll always give you the charge on the cation or the anion. This is not something that you're going to have to ever figure out. We also have polyatomic ions, so it's not just one atom, it's multiple atoms bonded together, but they have a charge on them. Usually what you'll see is so this right here is an ion, the whole thing together, because it has 2 negative charges. Usually what you'll see in these kind of molecules or ions is that they are covalently bonded together, and they just happen to have a positive or negative charge, and that's why they are considered a polyatomic ion. An example is sodium nitrate, also nitrite, any of those. Okay. So when we're looking at ions, if we look at the periodic table, those in the same group, so all of these ones that are in the same group here have the same charge. So in group 1A, everybody has a +1 charge. In group 2A, everybody has a +2 charge. Over here on the opposite side, everybody in 7A has a -1 charge, 6A is -2, 5A is -3. Okay, so the ones that are in the same grouping have the same charge when they become an ion. Okay. In an ionic compound, you'll often see the chemical formula written out. And by looking at the chemical formula, you can figure out what the compound looks like. Okay? Especially if you know that it's an ionic compound. So we want to have a 0 overall charge, and so our charges have to be equal to 0 when you add them together. So in this case, we have sodium chloride, also known as table salt. Sodium has a +1 charge, chlorine has a -1 charge when they become ions. If you add +1 and -1 together, you get a total of 0. So this is correct. 1 sodium and 1 chlorine together create a 0 charged molecule. Over here for lithium, we've got something different. So this lithium oxide is going to have, you're going to have 2 lithiums and 1 oxygen. So lithium only has a +1 charge. Oxygen has a -2 charge. In order to balance the charges out, you need 2 of these lithiums, 2 plus 1 charges to get our +2, 1 -2, and then you add those together and you get 0. That's the only way. If you had one lithium and one oxygen, you would have a negatively charged molecule here. We want a zero charge, so you have to have the two. Similar thing going over here with barium iodide. Barium has a +2 charge when it becomes an ion. Iodine only has a -1 charge when it becomes an ion. So you need two of these to balance out the charge on the barium. So barium iodide is BaI2. Here's another one that's a little bit more tricky. Aluminum oxide. Aluminum has a +3 charge. Oxygen has a -2 charge. You can't really balance those out unless you have multiples of each of these. So if you have 2 + 3 charges, you get a +6. If you have 3 - 2 charges, you get a -6. And then you add those together and you get 0. So the way that you come up with a neutrally charged molecule here is by having 2 aluminum and 3 oxygen. So how do we write a formula for an ionic compound? First, you got to identify which element is the cation and which one is the anion. Which one becomes positive, which one becomes negative. So we're going to start with this example with calcium and oxygen. Calcium is a metal, oxygen is a nonmetal. All right, so one thing that you can do is go to the periodic table and use the group number of your element to figure out what the charge is. So calcium is in group 2A, so it is going to have a +2 charge. Oxygen is in group 6A, so it is going to have a -2 charge. Now you need to figure out how many of each ion you're going to need to come up with that charge of 0. You want to have, for the whole thing, when you put them together, you want to have a 0 charge. So how many do you need of each to get that 0 charge? Okay. When the cation and the anion have the same charge, you only need one of each. So for this one, we have calcium that has the +2 charge. We have oxygen that has the -2 charge. These are going to cancel each other out, so you only need one of each. So our answer here is going to be calcium oxide with 1 calcium and 1 oxygen in our formula. When the cation and the anion have different charges, however, you're going to have to figure out how many you need of each number in order to get that 0 neutral charge on your final molecule. So let's try a different example. In this case, we're going to use calcium and chlorine. Calcium has a +2 charge. Chlorine has a -1 charge. +2 charge means that you need 2 chlorine anions in order to balance the charge. A -1 charge means that you only need 1 calcium to balance out the charges. So let's look at this again. We've got calcium has a +2, chlorine is -1. In order to balance out the charges, you're going to need 1 calcium and 2 chlorines. So you'll write it Cl and then 2 as that subscript. That means there's 2 of this particular atom in the formula. Okay. We always place the cation first and then the anion when you write it out. So the one that had the positive charge always goes first. The one with the negative charge always goes second in our formula. And then you use those subscripts to show you how many of each atom are in this formula or in this molecule. If it only has 1, you don't need a subscript. For polyatomic ions, they're going to act very similarly. So if instead of chlorine you had this hydrogen carbonate molecule or bicarbonate, HCO3-, this acts the same as a chlorine. So if we had calcium and then this molecule, you'd need 2 of these to go with your calcium in order to balance out the charges. Since calcium is +2, you'd need 2 of these to balance out the charge and make it 0. So they work overall just like one unit. Okay, so when a cation and anion of equal charge combine, you only need 1 of each. So in this case, we have sodium and nitrate, I believe. Sodium is +1. This is -1. You only need 1 of each, so then to get the overall 0 charge, so you just write it as is. Same for barium sulfate. All right. Let's get into the other kind of bonding, which is covalent bonding. So we have ionic bonding. Covalent bonding is a little different. This is where we're sharing electrons between 2 atoms. So there's several different types of covalent bonds. You have single bonds, double bonds, and triple bonds. In a single bond, 2 electrons are shared between the 2 atoms. So example here is a chloride molecule. 2 chlorine atoms are sharing these 2 electrons, and this is a single bond. For a double bond, they will be sharing 4 electrons. So this is an oxygen molecule, 2 oxygens together. They will share 4 electrons in order to fill their outer shells. So if you have 1, 2, 3, 4, 5, 6, 7, 8, in order to fill the outer shell and make it 8, they have to share more. For nitrogen, and on this one on the end, we have them sharing 6 electrons. So this is a triple bond. So we've got single bond, double bond, triple bond. Sometimes you might see our molecules represented in Lewis structures. A Lewis structure just shows you where everything is in the molecule, where all the electrons are, where the bonds are, what atoms are in the molecule. So over here we've got our water molecule, hydrogen, 2 of them. If you look in the formula, it says 2 H's, 2 hydrogens, and 1 oxygen. So we've got 2 hydrogens on the outside, we've got our oxygen on the middle. We have some bonding here. These are covalent bonds here between the H and the O. They're sharing electrons. And then oxygen also has some extra valence electrons on the outside. In this case, it has 4. All right, so if you are counting the number of electrons on the outside of this oxygen, you count 2 for this shared bond, 2 for this shared bond, and then 1, 2, 3, 4. So we have 2, 4, 6, 8 electrons on the outside of this oxygen. So it has a full shell, and so it's nice and happy and stable. These are other ways of drawing Lewis structures. So you can see that this whole thing, this nitrate molecule, has a minus by it on the outside here. This shows that this particular ion, or this molecule, is a negatively charged ion. It's an anion. By putting those brackets and the minus sign here, we know that this is now a negatively charged ion. Carbon dioxide here also shown with our bonding. So we've got these double bonds here. If you remember, these are 4 electrons that are shared. So if you have 4 here and 4 here, that's a total of 8 around the carbon. So it's happy. We've got 4 here and then 1, 2, 3, 4 there around the oxygen. So it has 8 around it and it's happy as well. Now the molecules are not always going to look like in a straight line. Sometimes you're going to have bent angles in our bonds between the molecules, or sorry, between the atoms. So they're not always going to be just one straight line across. sometimes you're going to see these different angles depending on how many things are bonded together. It really does depend on how many things are bonded together. You could have a linear molecule, you could have a bent molecule. That's kind of what water looks like. It's bent. You can have trigonal planar, so it's got some angles here, but it's a flat molecule. This is a tetrahedral molecule. We've got trigonal pyramidal. So we've got lots of different ways that the bonds can occur between the two atoms, so they don't have to be just one straight line. Why does this happen? Because sometimes there's lone pairs of electrons on some of these atoms. So if we're looking here at water, there's electrons here and there's electrons here, so you can't have, they take up room. So you have to have a bent molecule in order to have space for the electrons that are over here. So electronegativity is a measure of an atom's attraction for an electron in a bond. It tells you how much that atom really wants to hold on to electrons. Does it like to hold on to electrons, or does it not like to hold on to electrons? If you look at the periodic table, increasing electronegativity goes from left to right. Increasing negativity goes from bottom to top. So the ones that are over here in the corner, in this top right corner, these are the most electronegative atoms. These are the ones that are going to want to hold onto electrons the most. Chlorine, fluorine, oxygen, sulfur, these atoms here like electrons a lot. Whereas the ones way down over here, like sodium, calcium, these guys over here, they don't really like to hold on to electrons nearly as much. So these are the ones that are going to lose electrons. All right, here's some more shapes of different types of molecules. Gives you their bond angles, and here's some examples of different ones that look like this. And this kind of, especially this trigonal pyramidal one, shows you why. So, and the bent one as well. It has these electrons taking up space on that atom, on that central atom, and so the bonds can't poke their way into that space, so these have to be bent. So electrons don't always like to hang out around the atoms equally. So in a covalent bond, we're sharing electrons. That doesn't mean that the electrons are equally shared. Sometimes they are not equally shared between the atoms. When we're talking about that, we're talking about bond polarity. A nonpolar bond is one where the electrons are shared equally between the two atoms. And there's no slight charges on either atom. Everybody's happy. Everybody has enough electrons around them at all times. A polar bond, on the other hand, is one where electrons spend more time around one of the atoms. They like one of the atoms more than the other that's in the covalent bond. This places slight charges on each of the atoms, and it's usually shown as this little squiggly, I don't know if that's a sigma or a delta or what that is, but it's usually this little squiggly line with a plus or a minus. It shows you that this is slightly positively charged here. This hydrogen here is slightly positively charged. The oxygen is slightly negatively charged. Okay, and the reason for this is all due to electronegativity. Remember, we looked at how on the periodic table you see that some atoms like electrons more than others. Well, in this case, oxygen really likes to hold on to electrons. Hydrogen does not like to hold on to electrons nearly as much. So in this particular covalent bond, the electrons are going to hang out around the oxygen more than they do around the hydrogen. Since electrons are negatively charged, that's going to put a slight negative charge on our oxygen and a slight positive charge on our hydrogen, since they're not hanging out here that much. In order to call it a polar bond, the charges must differ by at least 0.5 units. So there needs to be a difference in electronegativity between the hydrogen and the oxygen of more than 0.5 units in order to call this a polar bond. So when you draw polar molecules, a lot of times you're going to have to draw which way the electrons like to go. And you use an arrow for this. And you only use the arrow if it is a polar bond. Okay, so if it's not a polar bond, you don't draw any arrows. Okay, so it's these silly looking arrows with the lines at the back. It shows you which way the electrons like to go. Okay, so in this case, electrons like to go toward the oxygen and away from the carbon. Here, the electrons like to go toward the fluorine and away from the hydrogen. Here, they like to go toward the oxygen, away from the sulfur. Okay. So, by drawing these, you can show which way the polar bond likes to favor, like which atom is favored for the electrons. And then again, you can put these little, if it is polar and they do have a charge, you can put these little slight charges on them. Okay, now if the dipoles cancel, so like the electrons like to go this way, the electrons like to go this way, those two things cancel out. So there's not like one way that the electrons they're not all going the same direction. Because of that, there's no slight charges on this particular molecule. Same thing over here. Some of the electrons like to go this way, some of the electrons like to go this way. They are all not going in one direction, and so there are no slight charges here.